and welcome back. Now let's learn about signals and waveforms, how to think about how these values, 0s and 1, might change over time. Oh my gosh, time. So let's start at the beginning. A clock is the heartbeat of the system. Our clock, this particular signal is a beautiful, if you've seen some of these terms before, I hope you've seen these terms before. You've got the idea of t, which is the period, which is the distance between a rising edge and the next rising edge. That's important. T and frequency are inversely related. So frequency is 1 over the period, and period is 1 over the frequency. Okay, and typically, roughly, these are in the period is roughly 1 nanosecond, and the frequency is roughly 1 gigahertz. If the period goes to 1/3 of a nanosecond, that would mean the frequency is 3 gigahertz. So think about that. We've got voltage, so this is our clock, and it's going to vary between 3 volts and 0 volts, and we're going to treat these as 1s or 0s. So this is, again, abstractly thinking about these ideas. Signals are transferred over wires continuously, and there's delays. It takes time to go from here to there. So we'll talk about that in a little bit. We're going to treat them mostly as instantaneous, because mostly we're not talking about a long transmission, but as you actually get the distance between these signals to be great, it ends up being a real issue. In fact, Grace Mary Hopper used to walk around with a piece of wire about this long and saying, this is a nanosecond, because it takes this long for a signal to start here and get to that distance if you work out the speed of light. So remember that. And also remember that a wire can only have one value at a time. A single wire has one value at a time. You have multiple wires. Optical things, you can actually have multiples, single optical channel, you can have lots of signals, but in a physical kind of copper wire, you only have one signal at a time, okay? So here's an example of an adder circuit. As we're going to start thinking about these block diagrams, here's an adder. Look at this. I've got n bits of B, n bits of A, and I have some number of bits of this circuit. Now, if I look at this, let's look at it B0 and B1. There's some interesting things. These things are going to change over time. So this is voltage over time. I'm looking here, voltage as a function of time. And I'm seeing that voltage, here's my clock, a nice, very pretty clock, nice square wave in the bottom. But you're seeing there's some issues here. This is not a perfect signal here. This does not line up. Like, here's my lineup. It doesn't line up perfectly. There's some issues here. And it's also wiggling up here. We're going to see that there's imperfections. We're going to try to work around that with our signals as well. So we saw that they're noisy. They're not always perfectly flat, and they don't line up. There's a delay. There's a delay in just all the processing that has to be done in this circuit before the output. And maybe look at this. This is a delay on the input. The delay of the input is not even coming in here. Who knows how long this circuit delays and whether the output is even more delayed, if the output might even be more delayed, how that is. So we're going to have to deal with all of those challenges between noise and delays. This is real world, folks. This is a little harder. So yes, it's digital, but there's some issues we have to think about as we start to build our circuits together. Let's talk about some names. So here's a nibble. I've got here 4 parallel bits, x0 through x3, okay? And each of these, it'll be nice for this picture, there'll be no delays. Each of these has a value. When it's high, we're going to call it a 1. When it's low, we'll call it a 0. So now you see this path. This is kind of cool. X0 has different values, hopefully synchronized with the clock. 1, 0, 1, 1. X1 has 0, 1, 0, 0. Now here's the cool thing. Take your head and turn it sideways. And what you see is we turn it sideways. Now I'm looking sideways at this number. Here we go. Now that's the high order bit. That's the MSB, or most significant bit. And this is the LSB, or least significant bit. And if you draw it like that, here's the LSB, and here's the MSB. If you draw it like that, look, I'm seeing 0, 1, 0, 1. That's a 5. 0, 1, 1, 0. 6. 1, 0, 0, 0. 8. I memorized the whole, I hope you memorized that, by the way. 0, 0, 0, 1, 1, and 0, 1, 1, 1, 7. So I can just think about this as a big capital X, like a vector X, which is really a vector in some sense, and capturing, I draw it like this. I draw it like this looks like a chiclet. I draw a little chiclet saying this has the value 5. and the value is 6. And that saves me from having to draw 4 lines over time. I just draw the value x and its number over time, which really encodes the fact that there are really 4 bits doing the work, but I'm going to draw it like this x to make it really very convenient, okay? So think about that to group this. The point of this is to group my 4 bits into one kind of 4-bit wide vector. So now I can think about that. Now here we go, an adder. This is called a nibble adder. Look at that. 4 bits of A come in, 4 bits of B come in, and A plus B is represented on the output C. Sometimes 4 bits can't be enough to do that. That's when overflow would happen. But for now, let's pretend that overflow isn't happening, and A and B are going to be small enough there's no overflow. So that's what we got. This is fine. So that's pretty cool. So here's my A vector, here's my B vector, okay, both nibbles. And again, we just saw this last slide. A is we thought of as this 4 signals, A0, small lowercase A0 through A3. And now I've got 2 and 3, and 2 and 3 should add to 5. But what I'm noticing is there's something called a delay. Now I'm finally realizing that the fact that, this is real world, there are delays. It takes the time takes the time for some magical genie inside to do the work. We're going to see what the magical genie is when we build it ourselves, but to do the work, okay, 2 plus 3, 5. Okay, it takes me some time, it takes the genie some time to do that. So there's going to be a delay between when, for example, here's a new 3, here's a new 3, here's a new 10. When does the output C say 13? Well, it still says 5, even though right a moment after this time, I knew at that time that it was 3 and 10, but it took some time there, and we're going to call this the time between when the clock goes up, really usually when the clock goes up, till, or when the inputs change, I'll say inputs change, till I see the output, the correct value on the output. We're going to call that the adder propagation delay. And if this is an adder, we call it adder propagation delay. If this is a and, it would call it the and propagation delay. It's whatever the name of the block is, propagation delay. That says there's a delay between when the inputs are stable at their new values till when I can confidently say that the output has the correct value for whatever it's trying to calculate, okay? So new word here, adder propagation delay. Pretty cool, okay? So let's keep playing with this. As I start to have more and more complex signals, systems, I'm going to have a ton of signals. And boy, does it help to actually have a tool to look and see what's going high, when, what's going off. Oh, look at this. They're never supposed to be both 1, but look, right for that little instant, they're both 1. That can be a problem for my system, whatever it is. So as I'm building these systems, you need to have a piece of tool, a debugger, that will let you work with the signals in parallel, see all the signals in parallel, and be able to play with them. In fact, notice this. This one, look at this. Here, they're thinking about this as values, not as this. Here's the kind of the vector. Sometimes you want to see the actual bits, but you also sometimes you want to see the vector. So these debuggers often let you cluster them or not cluster them. It's pretty cool. Okay, that's kind of neat. So, big picture. There are 2 kinds of circuits we're going to look at in this series of lectures and in really computer engineering. We can categorize them to 2 ways. Kind number 1 is combinational logic circuits. These, if you took CS10, these are just like pure functions. Just like pure functions. This is also from 61A. It's a function that has no side effects, no state, it's memoryless. The output is only a function of the input. Combinational logic circuits, we love them. Very easy. Here's a set of inputs, and here's an output. There might be a delay in my combinational logic, but there's no feedback, there's no state. It's just output is only a function of the inputs. I'm ready to go. And our adder was like that. Here's some bits, and here's the output. It's always going to be the same output for the same input. That's the other critical piece of it. Or we also care about state elements. And state elements are ones that have state. They have memory. Boy, if I didn't have memory, my computer wouldn't be able to store the data that I've created. So we need state elements to store our data, registers, caches, memory, disk, all these things have state. They remember what you put them there. And I have combinational logic to do some calculations. And so we're going to have 2 of those kinds of circuits, and we need both of them in what we're going to be building. Okay, so combinational logic circuits are CL and state elements. Here's a circuit with state. And I haven't told you how it works, but I'm going to talk about what it is. This is called a register. You've seen a register when we were talking about RISC-V, but here is an example of what a register is. It has n bits of input, n bits of output, and it has a loader. And this little circuit says that something magical happens when that circuit goes high. So when that goes high, here's what the register does. I'm a register. I'm sitting here, I've got my outputs. My output is whatever I've been stored with. I have some value stored here, here's my output, okay? Here we go. Load goes high. I turn around, I grab the value of input, and I hold it. I remember it. And now I'm loading it. I'm loading this into myself, and now I ignore it. Once that goes high, I turn around quickly, grab it, and then turn around, and I hold that. That's what I hold. You gave me 5? Okay, here's 5. Holding 5. Oh, now it's changing to 10, 20. I don't care. I don't care what my input says because load is still low. Ready? Rising edge of load. Now it's a 7. Turn around, grab the 7, and 7. That's it. I'm holding 7. Now it's changing. Load is still low. Input is changing. I don't care. I'm holding it. Stable. State. I'm holding this 7. That's the idea. What often we do is we clock these devices. So now, rather than load going up every once in a while, I'm going to go up every single clock cycle. I'm here, I got my 7, and then clock goes up, turn around, grab whatever's there. Zoop, now it's a 12. Here's my, I shouldn't have said 12. Here's my 2. I don't have 12 fingers. 2. Okay, clock goes up again, whatever it happens to be. So there's a rhythmic nature to it, okay? And so normally we're going to clock these devices, and having them clocked is great because now there's a rhythm and now data's kind of moving in chunks, like an assembly line. Ka-chunk, ka-chunk, ka-chunk. They move to the next stage. Everything just kind of moves to the right and data. So that's going to be great as we build circuits. We're going to have our data kind of ka-chunk to the right. That's exactly what we'll use this register that's going to be clocked. So we typically clock our registers, not always, but we often do. In conclusion, clocks are the heartbeat, the pulse of our circuits. Voltages are analog. Voltages are, who knows what they are, but I'm going to quantize them. It's 0 to 3 volts. Next year, it's 0 and 2.5 volts, whatever they build. But I'm going to quantize them to be a 0 and 1 and think of them in a kind of soft, abstract way as a 0 and 1 from now on. Circuit delays are a fact of life. We saw that everything. There's real world natures. There's not just delays, but the values are often fuzzy. And one of the things we're going to do from our circuits is if the value came in fuzzy, like let's say it's a little bit below a 1, it's still a 1, but it's like not 3 volts, it's 2.5. We're going to make sure that circuit cleans it up. If every circuit cleans it up so that input was coming in was a little below 2, below 3, output is going to be solid 3. And the only way that they're going to have noise, the only reason it would not be 3 is then noise, or maybe there's some resistance on the line, so it had to go from here to here, and it started at 3, and it was lower by the time it got there. So the real world is going to influence this by adding noise to our system or having a distance with resistance across the line. But every one of our core blocks is going to try to clean the circuit up. If it came off a little bit higher than 0, we're going to clamp it down to 0. If it came in a little bit lower than 3, or a little above 3, we're going to try to make it clamp it at 3. So our job of each of these blocks is going to be clean the signal up, and then who knows in the transmission of that data to the next block, maybe your voltage got up, maybe there's some noise from the connection guide, maybe there's a distance and resistance, whatever it is. That might be not perfect 0 and 1 coming in, but we're going to try to clean up to be a 0 and 1 coming out. That's the idea of our blocks. And in summary, there's 2 kinds of circuits, combinational logic or CL, and state circuits like registers. We're going to learn more about those and even how to build a register in the next series of lectures. We'll see you there.